Okay, here's the gas laws. This video is on the build-up to the combined gas law, with a little bit of review of some of the other laws we learned. First, we learned Boyle's law, relationship between pressure and volume, and what we discovered doing the Boyle's law lab in class. We took this larger bottle, had some air in it, put a syringe with a certain volume and air, so the blue dots in the syringe, and then closed it. Okay, measured the pressure. That'd be our first pressure, and then we measured the volume of that syringe. Okay, so those are our first set of variables. Okay, and then we increased the pressure in this closed system of this bottle, and we did that by adding more particles. So we pumped it up with a bicycle pump, putting more gas particles into the bottle. And those gas particles now have less room to move because there's so many of them. They bump into each other more. And they bump onto the side, and they put that force on the area of the bottle. And they also do the same thing to the syringe. So they're pushing on this end of the syringe, and so the volume of the syringe goes down, pushes it down. So now that same amount of volume that was in the syringe before is in there, the blue dots, but now there's less movement. So the pressure inside increases. And so this is a inverse relationship where a direct relation, inverse relationship where when the pressure goes up, the volume goes down. Okay, so this second set of pressure would increase and this second volume would decrease inside the syringe. Okay, I'd like to show you this visually, right? We can think about this simulation here where we have some pressure and related to some volume. So here we have some particles. I'm going to change the particle. These are helium. If you notice, there's two little circles. Hydrogen. I'm going to change this to helium. Helium is a noble gas. It doesn't bond to other things. So those are just single atoms. That's why I describe them as particles sometimes, because it depends on what the gas is. Helium is an atom, so whereas hydrogen is a molecule. The diatomic molecule always bonds to another hydrogen. That's why we can say particles. All these little things that are all one entity. Okay, and so here's our pressure, 1 atmosphere. Temperature down here, 273 Kelvin, 0 degrees Celsius. Here's our volume. If we let's make the pressure so that the pressure is constant here. Or we can be looking at the pressure. If we were to decrease the volume, you notice that pressure is going up. Here, let's change this to as I decrease the volume, that pressure increases. So they are inversely related to each other. You can see that those bar graph going up. And one goes up, the other goes down. Right? That's the inverse relationship. When we look at this Charles law, this is that direct relationship. And so I can show you that here, where if we're looking at the temperature and the pressure, the volume, temperature and the volume. If we increase the temperature, make those particles move faster. Can you see how the speed of those particles is increasing? They're moving faster, which increases the pressure. But in this case, the pressure is going to stay constant because the volume of our container can change. So put it up all the way to this high temperature of 500. There's our temperature going up. Here's our volume is increased all the way to past 20. So if we decrease our temperature here, it gets a little colder, right? Those particles are moving slower. So we can look at that here. In this box, this is represented as these particles moving slower with the shorter arrows. You can think about what temperature means. Temperature is a measure of the speed of the particles. Okay, so here we're showing these. You can think about we learned about speed. We learned it as a vector, or the velocity. We learned it as a vector. When we use forces, we use it as a vector. You can think about these arrows would be how fast they're moving. So they're moving not as fast here. Here they're moving much faster. And so if the container can't change, the pressure is going to increase. If the container can change, like the bottle here, the volume is going to change. Okay, because it's going to equalize the pressure inside the closed system and the outside. if the volume can change. Okay, a couple of things to think about. Here's the relationship, is that when you're using temperature, it has to be in Kelvin. I don't know if I can say this enough, because we're dividing by temperature. So we can't use 0 degrees Celsius, Fahrenheit. So you can't have negative. It's gonna really alter this relationship. It's not gonna be a absolute relationship. So to change from Kelvin to Celsius, you add this number, 273.2, and that changes it from Celsius to Kelvin. If you want to go from Kelvin, then you would subtract 273.2. You do the opposite, right? Good old mathematics. So here they are. The laws. Pressure and volume, Boyle's. Okay. Volume and temperature, though, that is Charles. Okay. We're not going to really get into this relationship. We could look at this, and you can think about this as well. We kind of just showed you this is the pressure temperature. We're not going to go over this specifically, but this is called the Guy-Lucet law. It's just a relationship between pressure and temperature. And so you can see that as we increase, if we're looking at this, if we increase the temperature, right, our pressure is really going to increase. So those are direct relationship. Increase that temperature, pressure goes up, right? You see it's not a 1-to-1 ratio, but it goes up a little bit there. So that's the Guy-Lussac. We're not really going to get into that too much. This is another law where you're looking at the relationship between volume and the amount of gas. This is called Avogadro's law. And so this one you've experienced many times before. This would be like have a flat tire on your bike, and so you pump more gas into it, right, which increases the volume, makes it nice and hard. So they are a direct relationship also. What we're going to do is we're going to work on this law that's the combined gas law. Okay, so what we're going to do is we're going to take some principles here and put them together. Okay, we're going to take the Charles law. Okay, we take the Guy-Lussac law, the Boyle's law. We're going to combine them all. Okay, so here we have Boyle's law, pressure and volume. Here we have Charles' law, volume and temperature. Well, if I take this, you can see that first variable, we put that in there because volume and pressure is still going to be inversely related, but now volume and temperature are going to be directly related. Here we have pressure and temperature 1, so we can add those in there. Those are going to be the same thing. You could add those in there if you wanted to, not. But you can see it's already there, P and T. Same thing with the 2's. We can add these into this. Our pressure, okay, it would be the same relationship with temperature here. So this is our combined gas law. It's the pressure variable 1, volume variable 1, and then temperature variable 1. It is equal to the same relationship, the P2 V2 over T2. Okay, so this is our equation. Alrighty, that's the combined gas law. Putting them together, and so now we have. That should be on top of there, but it's all right. There we go, so you can read it. Now we're going to do some math with these laws. So now you're going to have 5 variables, 1 unknown. So you can use. So when you're doing this, you want to solve for your unknown, which I'll do in the next video with an example problem.